In this video, we will continue our look at nucleophilic acyl substitution, focusing on intramolecular Claisen condensation, as well as nucleophilic acyl substitution by other enolates. Here we have an example that starts with a diester, and if this is treated with an alkoxide followed by H3O+, we can isolate a new product. Let's see what happens. Methoxide can abstract an alpha proton from this position or from this position. This compound is symmetric, so it doesn't matter. So let's show the formation of one of these enolates. That will give us this. Let's make this easier on ourselves by numbering our carbons. And you'll notice here we have our nucleophile, and within the same molecule we have our electrophile. So this nucleophile can share electrons with the carbon, push these electrons up onto the oxygen. So let's say this is our carbon 6, which is connected to an O- and an OCH3. 6 is connected to 5, 4, 3, 2. 2 is now connected to 6, and carbon 2 is also connected to carbon 1. So let's check this. This is 1, 2 was the enolate, 3, 4, 5, 6 was the electrophile that got attacked. Now these electrons can fold back in, kick out the methoxy group as a leaving group, and we end up with this beta keto ester. And we formed a new ring because both the enolate and the ester that got attacked were in the same molecule. Now this will also go through the favorable equilibrium step where this gets deprotonated, and then upon aqueous acid workup you will isolate this product. So this is an intramolecular Claisen condensation, and an intramolecular Claisen is called a Dieckmann cyclization. Dieckmann cyclizations will occur readily if it leads to the formation of a 5 or 6 membered ring. Typically, if you're trying to get intramolecular reaction rather than intermolecular reaction, you would carry out the reaction extremely dilute so that once you have your enolate, you don't want this to bump into another molecule. You want it to flop around and bump into itself. So Dieckmann cyclization. Finally, let's look at a few other examples of nucleophilic acyl substitution. So rather than combining a couple of esters, here we have a ketone and an ester. Well, this ester doesn't have any alpha hydrogens, so there's no enolate can be formed here, but our ketone can form an enolate. So methoxide can grab off a proton from here, and that will lead to the formation of some of this enolate. Now, self-addition to a ketone is not favored, so the major product will result from addition to the ester. These electrons go up, come back down, kick this out, and what we end up with will look like this. And what we have made is a beta diketone. In our second example, we have a compound that contains both a ketone and an ester. If this is treated with methoxide, this can grab off a proton from here, it can grab off a proton from here, and it can grab off a proton from here. So all of these enolates will be formed, but keep in mind that they are in equilibrium. So if we form the enolate at this position, then this enolate would add to a ketone. But we know that addition to a ketone doesn't work very well. If this enolate is formed, then it could do a nucleophilic attack on the ester carbon, but that would lead to 1, 2, 3, 4, 5, 6, 7, an 8-membered ring, and that's not easy to do. But if this enolate is formed, it could add here, and that would lead to 1, 2, 3, 4, 5, 6, a 6-membered ring. So let's focus on the enolate that forms here, and that would give us some of this. Now, this enolate can share its electrons with the carbonyl carbon. These electrons go up, come back down, kick this out. So here is our carbon that is a carbonyl. It's connected to a CH2, 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 CH2. This is the CH that was the enolate, and so this is also connected to the C double bond O and the CH3. So once again, we can have an intramolecular reaction where the enolate can react with an ester within the same molecule, and it gives us a beta diketone. And a third example, once again, we have acetone. We have a ketone reacting with, in this case, a carbonate ester. This one cannot form an enolate, but it is susceptible to nucleophilic attack. So the methoxide can grab off one of these protons so that we will generate some of this enolate. And self-addition to the ketone is going to be very slow and equilibrium is not favored. So instead, the nucleophile will add to this carbon, push these electrons up, and then they're going to come back down and kick out either one of the methoxy groups. So what we end up with is the CH3 C double bond O CH2 connected to the C double bond O O CH3. So in these cases, we made a beta diketone, and in this case, we made a beta keto ester, which once again could be used in the acetoacetic ester synthesis. So we are finding more ways to make some of the starting materials for other types of synthetic sequences. So the take-home point from this slide is that, yes, other compounds can be used to form enolates that can then react with an ester. It's important to watch out for competing reactions. We couldn't use an aldehyde, for example, because the aldehyde enolate would do self-addition as well as react with the ester. So you have to watch out for competing reactions. Now, what if you had available some propanal and some methyl propanoate, and you needed to make these two different targets? Now look at how different these compounds are. This one, we have a ketone that is beta to an aldehyde. Here we have an alcohol that is beta to an ester. So they look very different, they have very different structure, and yet they can be made from these two compounds. So let's look at each compound a little bit more closely. If we're looking over here, well, this could be what came from the ester that got attacked, and then this would be the piece that was the enolate that did the attacking. So this was the enolate. It was therefore the nucleophile, and this is derived from the aldehyde, whereas this must have been the electrophile, and this was the ester. So to make this compound, we need to start with our aldehyde, treat it with LDA to make sure we don't have aldehyde left over that could do self-addition, because we only want it to react with the ester. So if we start with the aldehyde and we treat it with LDA, we are going to make some of this enolate. Sorry, we're going to make lots of this enolate. And then when we add in the second ingredient, our ester, this enolate will do nucleophilic acyl substitution. So this will add here, push these electrons up, back down, kick out the methoxy group. So we will get this as our product. So the aldehyde enolate carried out a nucleophilic acyl substitution on the ester. If we look at our second target, well, here we have the ester and here we have an alcohol. Remember, an alcohol is formed when a nucleophile adds to the carbonyl carbon of an aldehyde. So that means this was our aldehyde, and this was the electrophile that got attacked. And then this one was the enolate, this was the nucleophile, and this was the ester. So in this case, we would start out with the ester and treat this with LDA, and that will give us some of this enolate, mostly this enolate, so that self-addition doesn't happen. And then when we add in the aldehyde, now this enolate can do nucleophilic addition, and there's also a proton transfer step, but that is going to give us, let's see, CH3, CH2, CHOH connected to the CH that is connected to the CH3 and to the C double bond O, O, CH3. So it's written differently, but this is the same as this. So as you gain more and more practice looking at the products of aldol addition and Claisen condensation, you're really looking at nucleophilic addition and nucleophilic acyl substitution. The more practice you get with that, the better you'll be able to look at a target and figure out what you need to do to get there. Mixing together different aldehydes, or reacting together different esters, or reacting an aldehyde with an ester, reacting an ester with an aldehyde, reacting an ester with a ketone, right? There's a lot of flexibility in terms of reaction products. So the more practice you get working forward, the better you will get at working backwards.